Okay, so everyone's here because there's one empty. Wait a minute. Nope. No. Sorry. Who are we missing?
June. June. The other Korean officer.
Excuse me?
The other Korean officer. June.
Oh, I don't know him there. Okay, well, it's time anyway. Okay, so the first lab is tomorrow, right? 8 to 10. Usually the labs don't last 2 hours. Usually it's less, okay? So you want to be there promptly on time. Jay will introduce the lab to you. I'll be there too. Okay, there he is. So, because we now have 13 students, there's going to be one group of 4. We're going to have 4 groups. 3 of the groups will have 3 students. We'll have one group of 4. It looks like this is the way it's going to be for this quarter. Okay, you guys work it out, and you can change groups from experiment to experiment. Okay, the distance learning students, I think we're going to have 4 or 5 students per group. Yeah, because there's just so many of them. Jay has done some years ago, maybe Gene a couple of years ago, or maybe 3. Jay did videos. The introduction you're going to get from Jay to the experiment tomorrow, he's made videos of all of those, and they're very popular. They were necessary because of distance learning students. So all the distance learning students should look at Jay's video. Sometimes he has more than one video for an experiment. They're all on. They should be on Sakai. I think we did that last week or 2 weeks ago or something.
Oh, okay.
I think. Right? What we found, surprisingly, was the resident students were looking at the videos. And we were shocked. We shouldn't have been, of course. So you guys can look at those. And you know, the advantage is you can look at them at your own time. You should still be there for Jay's introduction, okay? But we found that students are looking at, while they're doing the experiment, they're looking at Jay's videos, okay? That's fine. You know, you can run it back and you can go to the spots where you need to, where you're having trouble. So you guys are, you know, they're on Sakai, right? Okay. What else? What am I forgetting? Okay. I can't think of anything right now. Okay, does anybody have any questions about that tomorrow? Oh, so it'll be the lab reports, typically they're due at the time of the next lab. Not always. Because sometimes there may be 3 weeks between labs. Because Jay's going out of town, you know, so. But this experiment, the reports will be due 2 weeks from tomorrow. And that holds for the distance learning students too. Okay, and you guys need to schedule a time once you've got a preliminary write-up to come by and we can talk about it. I can look for trouble, because there's usually trouble, almost always. Trust me, I know I've been through this many times. I told you about this before, right? In the first day of class, remember? I know it seems like a long time ago. And the distance learning students, we're going to handle that by email or phone. We'll just have to wait and see. We'll try email. Okay, anybody have any questions about the lab or about everything? Okay, oh, the handouts. I knew that was something that was bothering me. We have handouts, of course, for each experiment, right? So those are on Sakai. You want to print those out, I think. Well, you don't have, it's up to you, but you want to be aware of those. I would look, again, for efficiency, like when we do homework, you should look through the handouts before you come to the lab. That helps. You're going to find you're totally confused, except perhaps for tomorrow's lab. It's pretty simple, as you will see. Okay, but it's good to just look it over, get it in your head, and you can be confused. This happens to me all the time. The first time I look at something, you know, I have no idea what's going on. I'm looking at a journal article or something, or it could be something even much simpler. And I go, oh, I can't understand this, but at least I give it a shot, and I go away for a while, and I come back, and then I look at it again. It's starting to look a little simpler, right? So you guys, you need to do this kind of thing here, because one of the ways that this place is different from a normal university is we don't have a lot of time here, okay? You have to graduate on time. This is, right? So we don't have that luxury of, oh, the research is not going well, I'll stick around another quarter. It's what happens at normal universities, right? We can't do that here. So you got to be efficient. So I would recommend that you look over the handouts first. Just get the ideas in your head. Okay, so I guess we're going to turn the lights off because that just doesn't look as good as I thought it should. But we have, yeah, it's much better. Whoa. Okay. So the first experiment is tomorrow, right? And it's appropriate to talk a little bit about the error analysis. Now, one of the things I need to tell you is, when I say error analysis, I mean quantitative error analysis. People often engage in qualitative error analyses. This happens anytime you're doing an experiment. Somebody will say, oh, look at this, what's causing this? This is an error here. We shouldn't be getting this value. This looks too high. You know, what could be causing that? And somebody will say, oh, it's probably this, and it sounds good, and everyone's happy, and they move along. Okay, there's a big danger in that, though. You can imagine what it is, right? And this happens all the time out there in the real world. People come up with an explanation for an error, a discrepancy, and it sounds good, right? But you never really know if it's correct unless you make it quantitative. And this happens all the time. People will say something that sounds good, that explains a discrepancy, but it could be just negligible. It may not quantitatively account for the effect. So in physics, we want to be careful with this, and that's the whole idea of quantitative error analysis. So the first experiment is a very simple apparatus. So it's really emphasizing, well, how we handle data, how we reduce data to get certain values out. And a lot of it is error analysis. Now, for two different experiments, any two experiments that are different, the error analysis is not going to be the same. You have to tailor it to the experiment. And you learn through experience that you don't want to go overboard on it, because error analysis is inherently approximate. It's very rough. All right? Now, we'll actually see some examples. I'll try to remember to point out to you later. So you don't want to go overboard on it, but it's actually, when you're comparing, typically what we do in experiments is you have some experimental value and you're comparing it to a theoretical value. And you want to know if they agree. How do we know that they agree? Well, that's why we have quantitative error analysis, as you will see. I'll be talking about that. Okay, so here's the experiment. I was just talking to Jay a little while ago. He likes this. It's really easy to set up. He set it up while we were talking. This is a spring with a mass on the end of it, and there's a weight hanger here, and you'll be piling on different slotted weights, different masses here. And incidentally, what's relevant here is the total mass. You want to make sure you include the mass of the weight hanger. Okay, the spring doesn't know the difference. It's the total mass that you need to put here, right? And the idea is for different masses to see how much the spring stretches. And from data on that, we can determine the spring constant. Now you'll notice I've used K here, which most people use instead of KFCS is S, that they use S, but that you can handle it, right? This is what people normally use for the spring constant. Now this is a real experiment, and on our model system that we talked about in lecture, we assumed a massless spring. Remember that? There was no kinetic energy associated with the spring. Remember when I talked about that? Well, this is a real spring, so it's going to have some mass, and we have to take that into account. So you'll simply be sighting along here and taking meter stick for different masses, taking different readings here. That's the static data. You're going to take two types of data. This is the static, we call this the static data. You're also going to time the oscillations. We'll call that the dynamic data. And the basic idea of the experiment is you can determine the spring constant statically from measurements here, like I just described, and dynamically from the period you can determine. And we want to compare the two values. and see if they agree within experimental error. That's the idea. Any questions? Okay, so let's look at the static. Let's look at the static measurements first. Here's the idea. What you're going to plot is the force exerted on the spring, which is the total mass times g. That's the magnitude of the force. I put magnitude here because, you know, the spring force is opposite. There's a negative sign in Hooke's law. It's just to get rid of that. So this is basically what we call the hanging weight, which is equal and opposite to the force exerted by the spring. And you're going to get data here. Now, your actual data on this scale here, this graph, it's not going to deviate as much as I've shown it here. This is just in principle, almost always when you take readings of something in an experiment, there's going to be fluctuations, right? Random fluctuations. And incidentally, I should have said, that's what we're dealing with here is there's well-known ways of handling random error. Here it is, random error. This is error that's just due to the fact that things fluctuate, okay? Another type of error is systematic error. Systematic error is a constant error that's come in for some reason. The standard example people give is, imagine this is a meter stick, okay? And let's say somebody has deviously sanded down the end. Suppose the 0 doesn't correspond to the end here, but it's out here. Let's say somebody's shortened it just to cause trouble. Maybe a terrorist. Well, usually I'm sorry. It's just hard to get away from this stuff these days. Those terrorists. You're taking measurements. Now, I don't want you to think of this experiment, because in this experiment, what's important really are changes in distance, okay? But there may be part of the handout. I haven't looked at the handout in 4 years. When I was telling you guys to look at the handout, I was talking to myself too. I need to look at the handout, and I haven't done that. But the basic idea here, we're going to be looking at changes in distance. Where the origin is really not going to make much difference. But there is one case in this, one part of this experiment, sort of an isolated part, where I think it does make a difference, but I can't remember because I haven't looked at the handout. I should have. But suppose we're doing some other experiment where the origin makes a difference. We have this meter stick that somebody has sanded off here that we can't tell. Now, okay, I know what you're thinking. They usually have these brass clips on here to thwart the terrorists, right? We could go on with this forever, can't we? But let's just suppose it's an older meter stick, or this brass clip has fallen off or something, or it's been removed. You go in here and you make these measurements, what's going to happen? You have a systematic error. It is systematically giving you smaller readings than the real distance, okay? So that's a standard example of a systematic error. And systematic errors are tough to handle, and they happen. And you just learn to deal with them. You know, in acoustics, for example, if you don't pay attention, the speed of sound depends upon temperature. And if you don't pay temperature could have changed during some experiment. And if you don't realize that, you can get into trouble. But most acousticians learn this. They learn it the hard way. Okay, and they pay attention to temperature because they know it's going to change the speed of sound. But there are many examples. And sometimes some systematic errors people have never uncovered. Sometimes you can't understand everything in any experiment. Somebody told me that a long time ago when I was a graduate student. I've never forgotten it. It's true. Even simple experiments, there can be things can happen that you never really can fully explain. And a lot of times it's associated with systematic error. You say, oh, there's some systematic error came in here, let's retake the data and now everything's fine. What was it? We don't know, but let's just move on. Okay, this is reality. Experimental physics here is reality. This kind of thing happens. But handling random error is well understood. And I should have written it down in here. The mathematical theory behind error analysis is called probability and statistics. From the theory, maybe some of you have had that before, probability and statistics. So error analysis, the formulas that we use, the way we handle error analysis, the way we deal with it mathematically, has a proper, rigorous mathematical foundation called probability and statistics. Probability and statistics. Okay, so here's the data here. Because of Hooke's law is usually highly valid springs, the data should lie in a straight line here, but there will always be fluctuations just due to the meter stick readings here. This is even for a perfect meter stick, you know, with no problem with the end here. There's going to be fluctuations when you take the reading, because the graduation's you can only read it to some scale, right? Typically some fraction of a millimeter. It's graduated in millimeters, right? And you should probably estimate, you know, this is left up to you, and it's probably in the handout. I wish I'd read the handout. You could probably estimate to the nearest third of a millimeter or half of I think you can do a half of a millimeter. Going to the nearest, writing down data to the nearest millimeter, does that sound right to you? No, I don't think. Koreans know because they're in the metric system. No, everyone knows what a millimeter is, right? It's something like this. Yeah, you should be able to estimate the fraction of a millimeter. You should do that. And it takes a little bit of practice, but you should do that. All right. So what do we do with this? Well, Hooke's law tells us this is the effective unstretched length of the spring here. The force is proportional to the displacement of the spring from its unstretched state. And so this is our statement of Hooke's law here. We can see that we've got, you know, forces on the y-axis, x is down here. If we plot the data like I've shown here, and we find the best fit straight line here, we can get that will be the value of this. It's our best estimate of the spring constant, right? So we're going to call that static, K sub s for static. And you've all probably done this. You're going to plot this using software, and you're going to use a least squares linear fit, or it's known by different names. Has everyone done that before? If you haven't, that's okay. This is why we have this experiment, just to make sure you understand. You can use Excel, you can use MATLAB. All students here take a MATLAB course, right? Yeah. I don't use Excel, okay, but people have done it. But even MATLAB, there's trouble with this. There's ways of finding the best fit straight line. Okay, in MATLAB and in Excel. Sometimes in Excel you have to turn it on. Does anybody have any experience with this? If you have trouble with this least squares fit, let me know. I do have some documents on my computer regarding this, on how to handle it from the past when students have had trouble. Now for the interesting part. Everybody knows about this, right? There's some uncertainty in the slope, obviously, right? The technical name for that is standard deviation. When we write down the slope here, it's going to be plus or minus something. Technically plus or minus the standard deviation. But this is a measure of the uncertainty of this value. How do you get that? Well, the answer is the routine, the software, what's in the routine that calculates this best fit. The calculations it has to go through, it's one minor step to get the standard deviation or uncertainty here. And sometimes getting that out of the software can be trouble, okay? So we'll deal with this. But the software I use, Origin, you ask to find the slope, with it gives you the uncertainty. It tells you that, which is what all graphic spreadsheet software should do. All of it, okay? But I don't think that's the case. All right. So we now have a measure of the spring constant with some measure of the uncertainty. And we're not going to worry too much about this, but rigorously speaking, this is a quantity called the standard deviation. And the meaning of the standard deviation is, I've forgotten, is the correct value. There's a certain percentage, 60 some percent. Anybody remember?
7.
Well, it has to do with what's called a bell curve or a Gaussian curve. I wasn't planning on talking about this, sorry. Suppose we're measuring something here. This is some variable x, or in our case, it's going to be the slope, this k sub s. And this is just the probability or the number of, I shouldn't have gotten into this. Let me go back. Let's speak of this in general. Here's some x, some value x that you're measuring. If you imagine taking many measurements of x, due to random error, you're going to get, almost always, what you get here is a Gaussian curve, also called a bell curve. You've all heard of a bell curve, right? Okay. So the best value of x is going to be, when you need a lot of measurements to believe in that, is going to be here. This is the average value. Let's just call it the average value. Okay, but there's some uncertainty. Each time I go in and measure x, I can get anything around here. It's unlikely I'm going to be over here, right? So the standard deviation is defined, and I need help on here. Somebody knows this. James, do you know this? What?
Not off the top of my head.
Well, does somebody get on the internet? You guys are. Okay. It's usually called, this is the standard deviation, okay? And technically, it's what I'm calling the uncertainty here. And we don't really need to get into this unless we get real quantitative about the error analysis. We just need some measure of the uncertainty here, okay? But from a rigorous point of view, what you want to put here is the standard deviation. And the meaning of the standard deviation here, called sigma, is that the probability of, when you go in to make a measurement, the probability of being from here to here is like 68% or something. What is it, Robert? Have you found it? 68%, okay? Sorry, I wasn't planning on doing this, but maybe I think it's a good thing, because that's the technical meaning of what this is. So, when the software gives you a slope with some uncertainty, it's giving you the standard deviation. It's an approximate value of the standard deviation, incidentally, right? There's a standard deviation of the standard deviation. This stuff never ends. Error analysis never ends. That's why you don't want to get caught, you don't want to be swept away by it, okay? You want to keep a proper perspective on error analysis. It's rough. Okay. All right, any questions so far? All right. Now, dynamically, we measure the period. That's got to tell us something. What can we get from that? Well, let's go back and look at our theory. Remember, there's no omega naught here, I dropped it. But this is for simple harmonic oscillator, the square of the frequency, angular frequency, is k over m, right? Now, what is easy to measure here is period. You're going to time, like I did in class, right? You're going to time, not one oscillation, because the percentage error can be huge there. You're going to time like 10 oscillations or 20. I don't know, it's in the handout, suggested. And it's flexible, you can do what you feel like doing. You're going to time like 10 oscillations like I did in class, and divide by 10. By timing many oscillations, you're going to be more accurate, more precise. So you're going to get the period. Remember, the period is 1 over the frequency, and the frequency is omega divided by 2 pi. So the period is 2 pi over the angular frequency. So we can combine these two. We can get rid of omega here. Not a useful quantity experimentally. It just hardly ever, if ever, is. We get rid of it, and then we have an equation here. You can see it. You can do this in your head. We get this. And now what we can do, the idea here is to find the spring constant dynamically in a different way and compare it to that value. So we can solve this for k, and we get the dynamic k. simply from here. And do we want to do it just at one mass? Well, you can, but you're never going to know if it's right, or if something is coming in at different masses. So it's a good idea to vary this quantity, right? So we're going to do this just as we had to do at least 2 different masses, didn't we? Right? Why?
Get a line.
Yeah, get a line, right? So you could just do 2 points, but you can see the problem with 2 points, right? What if you chose these 2 points right here? You can see that it can be substantially off, right? Okay, so similar thing can happen here due to fluctuations. So we want to take different mass values. So if you do that, and you're going to do this, different masses with different periods, and you may even repeat the period measurement. Again, I didn't look at the handout, but often, and I'm getting this mixed up with the mechanics lab. That was the last time I did an experiment like this, was a couple summers ago, 1 summer ago, I think. So I'm not sure. But you can make this more accurate, not only by timing a lot of oscillations, but then repeating it. Time 10 oscillations, time 10 again, right? Without changing the mass, right? Okay, it all depends on how accurate you want to be, how precise. So what we would find here, we could plot. We'll get different values of k. This is one thing you can do. It turns out that's not what we're going to do here. But one thing you can do, for different values of m, you get these different values of t, and you can plot as a function of m. You can do that. What's supposed to happen? What should you get, according to the theory here? Right? Should be a, should be a constant. This is the spring constant, right? A constant. So it should be constant. Even though m's changing, t is changing too. You increase the mass, you're going to increase the period. And these shouldn't increase the numerator and denominator in such a way that you get a constant.
Shouldn't that be a straight line?
Something's not right here. Is that better?
Yeah.
Sorry, thank you. Okay, so if you plot this versus m, you should get this. And if you try to do that in this experiment, you're going to find that it doesn't work. There's some systematic error coming in. So don't do it. We're not going to ask you to do it. Instead, we're going to develop the theory a little bit here. The problem is the spring mass. Remember that? The spring, we can't always, it's typically true that you can't neglect spring mass in real systems. If the mass on the end, and how do I know if the spring mass is small or big? How do I know? Everything's relative, right? So what does small spring mass mean here? Small compared to that. It's the only other mass in town, right? So you know it's got to be true that what we mean by small, this is being small, is small compared to this. It's typically the case, though, not always, that the spring mass is relatively small. And people have done this theory. I've been through it. It's interesting. God, I wish I looked at the handout. I don't think we have this. Sometimes we would put something like this in the back of the handout. Has anyone looked at the handout? Is there somewhere in the back like an appendix on the theoretical calculation of the effect of spring mass on an oscillator? Oh, are we going to do a homework problem on this?
Yeah.
Okay, again, it's been 4 years since I taught this course. So thank you. So we're going to do this as a homework problem. We'll calculate it. And it can be done different ways. I think we're going to take an energy approach. We will do this. Thank you very much. All right, so here's what we're going to do. We can, that's what the theory says. When the spring mass is substantially less than the mass on the end. Otherwise, this is a hard problem to solve, it turns out. But when it is small, the effective mass of the spring is ms over 3. What do I mean by effective? I mean just what you might guess is, and what you would like to happen here. Instead of the mass on the end, we should be able to add some effective mass to take into account the spring. And you can do this when the mass of the spring is small. And the theory tells us, that we're going to solve this as a homework problem, that it's 1/3 the mass of the spring. Why is it, most students think that you should just make this the mass of the spring. Why is that an overestimate? What's happening here? Remember we got this spring, it's going like this. So the spring has mass, right? The mass of the spring down here is fully participating in the motion. What about up here? It's not. It's hardly moving at all. Okay? So we would expect the effective mass to be between 0 and the mass of the spring. Again, the effective mass is what we're going to add on to the actual mass to take into account the mass of the spring. And the theory shows you that it's this. Now, we don't want to, you can deal with different experiment. You can deal in an experiment, any experiment, you can have different perspectives and take data in a different way. What we're going to do is, we're going to forget this. And this is common, experimentalists do. So a lot of times there's a kind of tension between experimentalists and theorists, okay? And some people do both. I do both. But so I have this internal tension. But what experimentalists often like is to disprove theorists. That it just usually doesn't get better than that. Okay. So here's somebody who's done some long calculation that 3 people in the world can understand, you know, or want to understand it. And you come along and you do an experiment. You say, "Sorry, the theory's wrong." You know. So yeah, so it usually doesn't get better than that for experimentalists, okay? So that carries over into situations like this, and quite naturally. Let's just forget about this for the moment. Let's experimentally determine the effective mass. Can we do that? Yeah, you have to think about it a little bit, but here's the idea. Here's our equation that's valid when there's no spring mass, right? This is the hanging mass, total hanging mass. The idea is that we feel it's plausible that we should be able to add an effective mass to this to be able to handle the spring mass. So that's what I've done. From here to here, I've just simply added in this effective mass. Now, what can we do? We can take data. We can take this data, remember, period, as a function of the hanging mass for different values of the hanging mass. And now what do we got? Now forget this, right? We can still keep this as our variable. What am I going to plot here? Think. T? You can, and I've encountered professionals who've done this and it just annoys the hell out of me. What's the appropriate variable, dependent variable to plot here? T squared. It's staring you in the face. So you want to plot T squared. Now you could, and people do this, again, I've seen them do it. You could do this, but then you're going to end up with a curve, you know. The advantage of plotting T squared is the theory tells, our equation here tells us that we should have a straight line if we use T squared. So that's the advantage. This has been done for a long time, probably centuries, okay? So you could plot T and then you could use some graphic spreadsheet software to fit the curve. It's much better to just think a little bit. Straight lines are easy to deal with. And even though we have software that can calculate fits, It's nice to deal with a straight line because you can more easily see the deviations. It's clear what's going on when you plot the appropriate variable to get a linear. If you can graph the data such that it should be a straight line, you usually want to do it. It's usually a good idea. Okay, so now the data, of course, is going to be something like this, right? And you're going to analyze that. You're going to get, again, the best fit straight line, which is going to have some slope. Now, for mathematical purposes here, let's call the slope, just call it A, okay? Our equation here tells us that this is going to be, when you plot t squared versus m, it's going to have this slope. So that means we can find the spring constant dynamically. And this is the intercept, the y-intercept. It's equal to that. And that's going to give us the effective mass. So the bottom line here is if you do this, first of all, I got to tell you, you never know what's going to happen in an experiment. Yeah?
So in that case, then, we have 3 variables, right? Because I thought this was assuming that you plug in for the effective mass, the ms divided by 3. Your spring.
Okay, you're missing the point. The point is, forget this.
Yeah.
Let's determine experimentally. Let's see if the effective mass works experimentally. And if it does, now by works, I mean we get a straight line here. The spring mass, it's conceivable that you may not get a straight line here. We don't know that the data is going to fall in a straight line. But if it does, and you're going to find that it does, okay, now we can get an experimental value of the effective mass. And if the mass of the spring is much less than the typical mass we're adding onto this, and we get far from m over 3, then you can go tell a theorist that the theorist made a mistake without having to look at the theorist's calculations. Right? Okay. So you can do a number on this. You're going to do this. You're going to find the slope, and you're going to find the uncertainty of the slope, right? Which is the standard deviation. So that brings us to the next step here. We're not done yet. So we can get these 2 values from the graph. We need to get, if we're going to claim to the theorist that this m over 3, 1/3 the mass of the spring is incorrect, we need to get, we don't have complete certainty what this value is, right? Because the data is going to fluctuate here. We don't know, we're getting the effective mass from the intercept here, right? We're getting it from the intercept. There's going to be some uncertainty. So this ms value that we are getting, m effective, it's going to be plus or minus. There's some uncertainty here. Now you see the importance of this, don't you? We want to see if this is equal to 1/3 the mass of the spring. What that means is, does 1/3 the mass of the spring lie in this interval right here? M effective plus or minus that. If we don't know this, we can't make a statement on whether we've verified the theory or not. So this is a basic idea of error analysis, quantitative error analysis. Sometimes it's hard to do and people don't do it. Sometimes they just don't want to do it, to be honest with you, because you run into there's a lot of trouble doing it, quantitative error analysis. So it all depends upon how accurate, it depends upon the particular experiment that you're doing, how deep you get into error analysis. But you can see the importance here. This happens all the time. So how do we find this from our data? Well, let's first of all deal with this. This has some uncertainty because the slope has some uncertainty. The spring constant is calculated from the best fit slope, which has some uncertainty. That means this has uncertainty. This is called propagation of error. You may have heard of this before. Because there's error here, it propagates and it causes an error there, or an uncertainty. So how do we get this uncertainty? We need to know this, because don't forget we're going to compare KD to KS. And how are we going to know if they agree or not? We've got to know the error bars. Okay. Just like we're talking about the effective mass here. So the way to look at this is take a differential of this. We're interested in changes in uncertainty. Excuse me. Take a differential of this, and you just get this. All right? Now, it's almost always better in experiments not to deal with the uncertainty of a quantity here, in this case the spring constant, but to deal with what's called the fractional uncertainty. We want to take the uncertainty of Kd divided by Kd, and that's going to be a certain percentage. That's almost always how experimentalists think, percentage uncertainty. We can do that here. Here's our relationship. Remember this relationship right here? We can take this and put it underneath here, and this is what we get. And now look how simple this is. This says the fractional uncertainty in K is minus the fractional uncertainty in the slope. It says the differential, the fractional differential is minus the fractional differential. Uncertainties, we just care about the absolute values here. We don't care about the fact that it's going in the opposite direction. We just want to know the interval, you know. So in terms of uncertainties, we ignore this and we write this. So this says that the fractional uncertainty of the dynamic spring constant is the same as the fractional uncertainty of the slope. So with the software, the software is going to give you the best slope, and it's going to give you this standard deviation, which is the uncertainty of the slope. You can calculate. It's very simple. It has the same percentage, there's the same percent. It's very easy. Now, if you want to get this, you just bring this over here and multiply. If you want to find out the value of that. But it's usually good to look at things in terms of fractional point of views because it's easier to see. It's more transparent. It's easier to see what's going on. Okay, good. So that wasn't too bad. But now we got another problem. We need to find the uncertainty of our effective mass for reasons that I said before. Do you see the propagation of error here? There's an uncertainty in the intercept. So that's going to propagate, that's going to cause it. But do we know this precisely? No. So now we have two quantities. The propagation of error here involves two quantities that have uncertainties. How do we do the propagation of error? Well, I think the best way is to proceed with the differentials. If we take a differential, again, I'll show you how this works. We take the differential, and now we have two uncertain quantities. Okay. Again, we divide by where we started. Before we took the differential, we had this. We divide to simplify it, and we get this. And that's how the differentials obey. This is what the differentials obey. Now, here's the interesting thing here. We're dealing with random error. These uncertainties here, there can be fluctuations, positive or negative, right? So if you imagine taking a lot of data here, sometimes this is going to be positive, sometimes it's going to be negative, and similarly here, because this is due to random fluctuations. The worst case analysis, the greatest value you can get here, is when they add together. They both have the same sign. That's this, okay? So you can imagine this is that, and this is that. This is called the worst case analysis. This is appropriate for somebody designing a bridge that people are going to travel across. We all hope that they're using a worst case analysis, right? So you can other things you can imagine like that. What?
I said I'm more of a fair weather bridge designer.
So, but usually in science and engineering too, except in cases like that where you want to be absolutely, it's a matter of safety, right? In cases where it's not a matter of safety, we just use the standard deviation. We don't use the worst case. Here, what's the worst case analysis here? Well, you can't, this curve it gets really close to zero. This Gaussian here goes very fast to zero. But technically, you can get a measurement all the way down to near zero and up there. So the worst case analysis here, what do they use? Does anybody know? I'll have to be honest with you, I don't know, but I can guess. I think 3 standard deviations is my guess. Some of the distance learning students might have encountered this. But See, what's a miracle? There's an old joke about a miracle is 5 standard deviations. It's really unlikely to measure something 5 standard deviations away. So I heard this joke years ago, and I think it was 5. So for the worst case, I know what I've done before. I've had to do worst case analysis before. You know, eventually it's going to happen, right? I've taken just 2 standard deviations, but I think it's probably better. I'm hoping for the bridge thing, they're doing 3, okay? Because I know that I'm going to be the one crossing the bridge, you know, going across the bridge when it fails, right? Okay, that's just the story of my life. All right. So this is the worst case, but that's not really what we're interested in here. We want, you know, that doesn't tell us, this is so remotely, it's just such a small probability of finding a measurement out here. We want something reasonable like a standard deviation, okay? So this is the maximum. Well, we can look at the minimum. This is where these 2 things have opposite signs, but that seems like an underestimate, right? This is an overestimate, this is an underestimate. So the theory of probability and statistics gives us the answer for assuming a Gaussian distribution, and they add at right angles. And this is called quadrature. It's actually simple to remember. So the statement of probability and statistics is that when you have 2 uncertainties here, on the average, the way they're going to add is Pythagoras. We call this quadrature, in quadrature. So you can see it's in between the max and the min. So that's what we should do here. Okay, now you can bring this over here and actually get the value here in kilograms or grams, whatever you want. Now we know this. What's the next step? Compare to 1/3 the mass of the spring. That's what you're going to do. See if it's inside this interval. If it's inside that interval, then it looks pretty good. If it's just marginally, you know, if it's near the endpoints here, then you're not really sure. But if this is the effective mass here, and here's this interval right here, and it's out here like this, there's a problem. Something's wrong. The theory's wrong. The theory's wrong. The theory can't be wrong, incidentally. I got to tell you, many people have gone through the theory. Everyone agrees. So it would be, in this case, it would be the experiment. There's some systematic error that's come into the experiment. Okay. So I got really kind of swept away with this effective mass, but don't forget, let's not forget the more important point here is we've got KD. So the final thing you should do, we're going to do in the analysis here, is compare these 2 values. And the natural way to do this, and this is, I hit upon this decades ago, and I think educationally it's great. It's really hard to find it in the technical literature, okay? But I want you guys to do this because it's good. You want to do a 1-dimensional graph. And that sort of tells you why it's not in the literature. Why would anybody do a 1-dimensional, you know, you got to have at least 2 dimensions to graph something, right? Well, it's not really true. This is a 1-dimensional graph. This has no meaning here. This is all the possible k values. This is this is newtons per meter here, ticked off, right? And I've plotted, well, what you're going to do is you're going to plot the static k value. Now you could plot it right on top of this, but because nothing's going on this way, it's natural just to lift it up for clarity. That's the only reason. Okay? So you can think of this as really lying down here, but we're just lifting up so we can clearly see what it is. Here's the value of ks. Here's ks plus delta ks. Here's ks minus delta ks, right? And similarly, you plot that. And now you can see the advantage of 1-dimensional graphs. In this case, you can see very clearly how good the agreement is between the 2 values. In this case, sometimes people say because the average value here lies within the error bar here, that's a sign of good agreement. However, you can see that this average value lies outside that, right? So which is not a good thing. But at least it gives you some kind of a qualitative feeling for how well the agreement is. If you had something like this, right? If this were over here, there's something wrong. Something's wrong. right? It could be, in general, it could be the theory, or it could be your analysis of data. And again, without these are called error bars. Without the error bars, how can you say whether you have good agreement or not? You don't have a clue. Some students say, well, find the percentage difference. Okay, and that's a good thing to find. And then they say, okay, so if it's 3%, is that good agreement? 1%? You don't know. You don't know. It all depends on what these error bars are, and we're pretending that we don't, if we don't know the error bars. So you just can't go, and I've seen students, I know this comes up, you know, they say, well, if it's 50% error between these two things, oh, that's way off. Not necessarily. There could be agreement. It all depends upon the size of the error bars. It all depends upon the size of the error bars. It's all relative. Okay, one quick thing here. This is amazing. I can't remember who put this into the handout. It might have been me years ago. Here's the problem. Suppose you want to come up with the best value of K of the spring constant. The natural thing to do is to average these two values, right? Sum them and divide by 2. That's what everybody would say, most everybody. But there's a problem. We have the error bar is smaller here. We trust this value more. We need to weight this value. Instead of adding these and divide by 2, instead of multiplying this by 1/2, multiplying that by 1/2 and adding them, that would be the average, right? I would rather multiply this by maybe 3/4 or something, or 2/3, and multiply this by 1/3. We need to weight in favor of that. Well, this has been worked out. What probability and statistics tells us, I've never seen the derivation to be honest with you, is here's the weighting factor you want to use. So in our case, we have these, we just have 2 values, but here's just the general, let's look at this. We just have 2 values. The value we trust more, this is going to be, the value that has less uncertainty. In other words, more certainty. This is going to be smaller, right? So it's going to make its value more important. This is what we mean by weighting. W-E-I-G-H-T-I-N-G. So we're weighting, we're making this more important in the average than that one. And the problem here is that when you do that, you've changed the units here. You have to do this right. You need to normalize it with this. And actually, I was thinking the best way to think about this is, you see this sum right here? This quantity, you want to imagine putting it in the denominator right here. It's just a constant, it doesn't depend upon I. It's a summation over all values. Those are the weighting factors, and this is what you get. So I want you guys to do that. I'm pretty sure I was the one who put this in years ago. And I just found this. Maybe it was John Taylor's error analysis book. If you ever have error analysis problems, that's a good book to look at. He's well known for a mechanics book that's widely used in physics. It's a book with a picture of the train wreck on the front, if you've ever, okay. So I had to use it once. I was doing some analysis. I think this was back in the 90s. And it was an experiment involved high amplitude acoustic noise. There was a lot of fluctuations in the data. And we got involved in this heavy duty quantitative error analysis, and it went beyond my knowledge. So I went to Taylor's book. And it's a simple book. It's used, freshmen use this book. But it told me what I needed to know. It's the way it works. Okay, so anyway, what about the uncertainty of this? Well, you can look that up too. This is the uncertainty obeys this relationship. Here it is, right here. So I want you guys to calculate this, and you might as well plot it on top of the data, well, you can move it up here. Plot it. It'll be somewhere, right? It'll be here, but not halfway in between. Where's it going to be? A little bit over here, because it's weighted more there. And see what the uncertainty is. See what it all looks like. Okay, sorry I went over. Anybody have any questions? Quick questions?
Here's the lab as well.
Oh, it's in the information. It's 107. That's the acoustics teaching lab here. We use other labs, the anechoic. We're going to be doing an experiment next quarter in the anechoic chamber. We use underwater experiments ultimately in this sequence, but all this quarter, I think we're going to be in 107. It's just down towards the end of the hall.
Do we have to print out